The area under a graph are uniquely determined by the width and the height, which are uniquely determined by the subdivision of AB for the width and the choice of the value of x in each subdivision. This allows us really to do all the work on the real line without sketching the graph of the function. This is great because some of the function can be really complicated. Example. Now I'm going to approximate the area under the graph of the function f(x) equals x plus e to the x on the interval 1, 3 using Riemann sums with n equals 4 with right-hand endpoint choice on each subinterval, and I'm going to do it without sketching the graph because I don't need to. The length of each subinterval is b minus a over n. In this case, the interval is 1, 3, so it's 3 minus 1 over 4, and we get 1/2. I'm going now to do everything on the x-axis. And again, I'm not going to sketch the graph of f(x) equals x plus c to the x. We have to add 1/2 to 1, and we get 1 1/2, or 3/2 if you want. We add another 1/2, and we get 2. We do it again, we get 2.5, or 5 over 2. And we add another 1/2, and we need to get to b, which is 3. And we do. Now I'm going to count that I have 4 subintervals. 1, 2, 3, 4. Yes, I do. Now I'm going just to make a note to myself that I need to take the height using the right-hand endpoints. In the first segment, this is the value of the function that I need to take. It has to be f of 3 over 2. In the second segment, x equals 2, it's the right-hand endpoint, so the height has to be f of 2. In the third segment, I have to take the height as the function evaluated at 5 over 2. And in the last segment, I have to choose the height to be the value of the function at x equals 3. Now I just have to add everything up. Note before, you check that you have 4 chosen points. Yellow, blue, green, and purple. Yes, I have exactly 4. And here's the sum. A, the area under the graph, can be approximated by the sum of those 4 rectangles, even though I don't have rectangles, but I know that the width of each one is 1 over 2, and the height of the first one is half of 3/2. The height of the second one is half of 2. The third one is half of 5 over 2, and the height of the last one is half of 3. I can now distribute the 1/2, and I get that. But now I can even evaluate more because I have the function. So now I'm going to substitute those values of the x's in the function. F of 3 over 2 is 3 over 2 plus e to the power of 3 over 2. F of 2 is 2 plus e to the power of 2, and so forth. In this case, I was using calculator just to show you a little bit a taste of what we were getting here. So after I was using calculator, I got that this is about 26.57. We are going to repeat and approximate the area under the same graph as before, using n equals 4 as before. But now we are going to take the height of the midpoint of each subinterval. The midpoint of an interval is the average of the two endpoints. In this case, it's going to be really useful. So this is what we had before. Now let's average the endpoints of each of the subintervals to find the value of the x, which is the midpoint. It's 1 plus 3 over 2 divided by 2, and we get 5 over 4. The average here is 3 over 2 plus 2 over 2. We get 7 over 4. And here, it's 2 plus 5 over 2 divided by 2, and we get 9 over 4. And here, when we average, we get 11 over 4. Because the length of each of the subintervals is 1 over 2, you can also add 1 over 2 to 5 over 4, and then to 7 over 4, and then to 9 over 4. So there are a few ways to do that. You can also do kind of a common denominator and to write everything as over 4. So 1 is 4 over 4, and 3 over 2 is 6 over 4, and then it's easy to see that the middle of 4 over 4 and 6 over 4 is 5 over 4. Just find your own way out to find the midpoint. And here is the sum. The width of each one of the rectangles is 1 over 2, and the height is the value of the function in this chosen midpoint. So it is half time f of 5 over 4 plus half time f of 7 over 4 plus 1 over 2 times f of 9 over 4 plus 1 over 2 times f of 11 over 4. We can distribute the 1/2 to get that. And because we have a specific function, we can also go ahead and substitute the values in the function, and we get that. Again, I was using calculator just to get a good idea, and I have here in this case 21.19. This is only approximation. Example. Approximate the area under the parabola y equals x to the power of 2 on the interval 0, 12 using Riemann sums with n equals 3. The length of each subdivision is 12 minus 0 over 3 equals 4. This is the width of each rectangle. Again, even though this is an easy function to sketch, I'm not going to sketch it. The height of each rectangle is the value of the function in the required value of x. We are going to do it 3 times. First time, we are going to use the left-hand endpoint. In the first segment, it is 0. In the second, it is 4. And in the third, it is 8. Now, we can sum up the area of the 3 rectangles. The width of each one is 4, so I can distribute the 4. The first height is f of 0. The second is f of 4, and the third is f of 8. Because I have the function, let's substitute the function in. F of 0 is 0 to the power of 2, f of 4 is 4 to the power of 2, and f of 8 is 8 to the power of 2. And I get this. Now I'm going to use the right-hand endpoint. The right-hand endpoint of the first subinterval is 4. In the second it is 8, and in the third it is 12. The area can be approximated by 4 times f of 4 plus f of 8 plus f of 12. When you calculate the numbers, you get 896. Now I'm going to use the midpoint. The midpoint in the first segment is 2, in the segment it's 6, and in the third it's 10. So the area can be approximated by 4 times f of 2 plus f of 6 plus f of 10, and when I evaluate the number, I get 560. If you look at those numbers, they're very different, which means that n equals 3 is not enough. I have to take n to be much more than n equals 3. But also, if you look at those values, you can see that the midpoint, in this case, because of the shape of the graph, is maybe the best. So again, when n is small, the difference between the sums and the true area is so large that this is really not a very good approximation for the area under the graph. It is possible to evaluate the exact area of a region under a graph on an interval between AB by taking the limit of the number of rectangles in the Riemann sum to infinity. So the finite integral, which is connected to areas, is written like that. This is the upper limit. This is the lower limit. As you can see, this is the height of each rectangle. That's why we have fx in the notation of the finite integral. Delta x is the width of each rectangle. That's why we have dx. Because delta x, when n approaches infinity, is very, very small. So it is dx. And then we have the Riemann sum, so we have the sigma when I runs from 1 to n, which is the sum of the areas of the n rectangles. And then when we are taking the limit of n to infinity, we are getting that this is exactly the area of a region under a graph of a function which is never negative.